Hello everyone, welcome to another Stata tutorial video. In this video, I'm going to talk about how to estimate binary choice models using Stata. I'll cover three different basic binary choice models, including the linear probability model, or LPM, the Probit, and the Logit. The dataset I have here is the Mraz dataset on female labor force participation in 1975. We will be estimating the impact of various factors on a woman's decision to enter the labor force. We'll start out with the linear probability model. This is the most basic way to estimate probability. We're simply going to run a linear regression with the labor force dummy as the dependent variable. To do this, I'll type reg INLF for in labor force as the dependent variable. As the explanatory variables, I'll include number of kids under 6, number of kids over 6, and finally, N wife Inc., which is essentially the husband's income. The main advantage of the LPM is that it's very easy to interpret. To estimate the probability that a particular woman is going to be in the labor force, we simply plug in the numbers of how many kids there are and the husband's income, and we just add these up, just like we would do with any regression. We can get this using the predict command. I'll call this the LPM prediction, and we're going to use the XB option, just like we usually do with a regular regression. If I go into the data browser, I can see these predicted probabilities. One of the main weaknesses of the LPM is that we can get probabilities that are either negative or greater than 1. I'm going to sort the data by the LPM predictions. Once I do this, we can see that there are two people in this data set who have negative probabilities. That is, these two people have a combination of husband income and number of kids that sends the probability so low that it drops below 0. We can see what these two people look like, and we can see that they both have 2 kids under 6. And if we look at the N wife Inc. variable, we can see that they both have very wealthy husbands. Remember that this was 1975, and we would consider 73,000 and 51,000 to be very high incomes relative to the other ones that we're seeing in this data set. The Probit and Logit models will solve this problem for us. Estimating a Probit using the Probit command is very similar to a normal regression. We simply type Probit and then the variables just like before. When I run this, you'll see the output looking a little bit different than before. First thing you notice is the iterations with the log likelihood. This is Stata simply showing us the maximization of the likelihood function, which is what's going on under the hood here. Now, the coefficients with the Probit work a little bit differently than in the LPM. These are the coefficients for predicting the latent variable that is going to go into the normal cumulative distribution function. So if we go and predict using the XB command, we're actually not going to get the probabilities. We're actually going to get the latent variable. I'll call this Probit latent and use the XB option. When I go into the data browser, you can see that we have a bunch of negative and positive numbers, but these are not actually probabilities. Many of them are in fact negative. To get the actual probability predictions, we have to predict. I'll name this Probit pred. We now need to use the option PR for probability. When we look at this, these look a lot more reasonable. And what you'll immediately notice is that for these first two observations, we now have very low probabilities, but they're not dipping below 0, so that's a good thing. We can check that this is doing what we want it to do by generating a new variable that I'll call Probit check equal to normal of Probit latent. The normal function in Stata is simply the standard normal cumulative distribution function. We can now go in here and compare Probit check with Probit pred, and you can see that these are in fact identical. The Logit works very similarly. We simply type Logit and then go about everything just like before. When I run this, you can see that Stata is also using maximum likelihood to estimate these coefficients. The Logit is very similar to the Probit, the only difference being that it makes a different assumption on the distribution of the error term. In this case, a logistic distribution instead of a normal distribution. As such, everything is going to work pretty similarly for predicting. I can predict the latent variables using XB, and I can predict the probabilities using PR. If we check these out, you can see that in general, the Logit and the Probit give fairly similar predictions. We can again verify these predictions by generating a Logit check. You can name this anything you like, equal to logistic of Logit latent. Logistic is simply the logistic CDF. When we compare these, you can see again that they are identical. The last thing I want to talk about is calculating marginal effects. This is a little bit tricky with Probits and Logits because we don't have a linear function anymore. If we go back to the LPM and ask the question, what is the effect of having one more kid on the probability that a woman will join the labor force? Well, we can simply look at this number right here. When we add a new child to the family, the probability that the woman will join the labor force goes down by about 20 percentage points. Note that this does not depend on the husband's income or the current number of kids. It's completely independent of those things. In the Probit and Logit, that's no longer the case. The amount that the probability changes when a new child is added depends on the current number of both categories of kids as well as the husband's income. As such, to calculate a marginal effect, we're actually going to have to know the value of those things. Let's do this for the Logit. Let's think about a hypothetical woman who already has one kid under 6, one kid over 6, and a husband's income of $20,000. The current prediction for the latent variable will be, we'll first take the constant. Now, if we already have one child under 6, we will take this coefficient and multiply by 1. If we have one kid over 6, we'll take this coefficient, multiply that by 1, and add that on. And finally, we'll take the husband's income coefficient and multiply that by 20 for $20,000. Note that these numbers that I came up with, one kid under 6, one kid over 6, and 20,000 income, were arbitrary just for illustrative purposes. Once we calculate this, we get a latent variable prediction of negative 0.41. To actually calculate the probability, we need to put this into the logistic function. Now, if we were working with a Probit, we would put this into the normal CDF. And what we would get is a probability of about 40% that this particular person is going to join the labor force. Now, if we think about adding another kid to the family, we're going to have to go back to this original calculation, and where we have minus 0.886, we need to multiply this by 2 because we're going from one kid to 2 kids. To calculate the new probability, I'll put this new number into the logistic function. And the new probability we can see is about 21%. Now, to calculate the marginal effect, we simply subtract these numbers. And what we get is a reduction of about 18.4 percentage points. If we want to report our estimates of marginal effects, it might not be a desirable thing to go and just pick an arbitrary person with an arbitrary number of kids and an arbitrary husband's income. One thing we might be interested in doing is estimating the marginal effects for a so-called average person. One way that we could do this would be to calculate the sample means for the variables and plug in those values. We would do this by typing sum and then putting in our 3 explanatory variables. We would then take these numbers and plug them in just like I did before. And then for the marginal effect, we would add 1 to this number right here and calculate the difference. There is kind of a shortcut though. And the way that we do that is by taking advantage of the latent variable prediction. Luckily, we've already calculated the latent variable predictions for the Logit. Those were right here. Now, if I calculate sum Logit latent, this number right here will give us the mean latent variable prediction for everyone in our data set. Therefore, the probability of a so-called average woman in the data set joining the labor force would be logistic of this number. That turns out to be about 56.8%. If we were to add 1 child under 6 to this average person's family, we would get a new latent variable of the current one, and we go back to our Logit estimation, and we would subtract this coefficient for adding 1 more child. Now we calculate the probability using the logistic function. And what we get is about 35%. To get the marginal effect, again, we simply subtract these numbers. Thus, for the average woman in the data set, we would get a reduction in probability of being in the labor force of about 21.6%. We should point out, however, that the disadvantage of this approach is the so-called average person is not very realistic because you can't exactly have 24% of a kid or 1.35 of a kid. But this does give us a general idea of the effect of having 1 more child. That wraps up our discussion on binary choice models. If you have any questions, please let me know. Thanks for watching.